They're still waiting back there. Okay, so I think we're on. You can only see the top of my head. There we are. Okay, I'm shorter today. Back, there we go. Okay. What we want to focus on today, the last session we addressed polar type of things, and I would like it if we had more time to spend on that, but when you get into second year calculus, you'll use that quite a bit. So hang on to your notes, come back and look at these old DVDs or video segments if necessary on that material. Related to that stuff, all the stuff you've studied previously related to that polar, and then even some of the stuff earlier in the course is going to relate to this new topic called vectors. And that's what we're going to start talking about today. And we only have the luxury of spending about 1 hour and a half or so of class time on this. This is an extremely important topic for engineering, science kind of things, and I'll point out to you some really practical aspects of this. I think you'll enjoy it. There's hardly any real new math here. So what I want to do is in the first segment, I want to talk about the introduction to vectors and then a new type of algebra, very simple, as long as you follow what I'm doing, and I don't think you'll find it too hard, called vector algebra and associated graphs. And then we'll practice using it with some practical examples. Okay? Now, I want to go back to something earlier, though, solving a trigonometric equation, which a lot of people seem to have trouble with. So I want to spend the first few minutes today going back over a problem that was in the book that a number of people came to me with trouble on. So we'll do that, and then we'll get on to the vector material. So if you jump to the computer, or to the overhead here, this is problem 55 out of our textbook on page 493. 55 on 493, and it happens to be f of x is given to you as 3 sine x. And then it asks you a series of questions about this. It wants to know what the zeros are of this function. Zeros, you remember from college algebra, mean what? No, not where x equals 0, where the output value equals 0. So you're trying to find the locations where the output value, f of x, this result here, equals 0. So in other words, the x-intercepts. Okay. The second thing they ask for is, given that graph, they want you to graph it, and that at this point should be elementary to you. That should be like you can do that one in your sleep, I hope. And C is solve the equation f of x equals 3.5. Now this is where people were having some difficulty. This is almost an intermediate algebra kind of a question, except with a trigonometric twist to it. And then finally, I'm looking over there at the monitor. From the graph drawn in the results, determine the values of f of x such that f of x is greater than 3/2. So in other words, where is f of x greater than 3/2? So I want to do this real quickly. Finding the zeros. First of all, I'm going to do this second part, drawing the graph. Draw a sine wave. And they ask us to do it from 0 to 2 pi. So it's a half open interval from 0 to 2 pi, not including the endpoint. There's the graph, and the amplitude is 3. We all know that. And we also know the period's 2 pi, so our quarter cycle points are at pi over 2. Clear back at the beginning of the course. Finding the zeros. Piece of cake. What you would do is you'd be solving this equation. 3 sine x, the output value equaling 0. You isolate this, sine x equals 0. You ask the question, what's the angle in here that happens to have a sine reading called of 0 value? Now, this you know is a function. Back to the unit circle and our inverse function. From minus pi over 2 to pi over 2 on the inverse sine. You can go back and review the material on the inverses if necessary. You can see that this reading is 0 right here at 0 radians. graph of that inverse function looks like this. Up to pi over 2, and as low as minus pi over 2. And domain from -1 to 1. So answering this question, the ratio reading is 0 right here at 0. So this would be at 0. And then these are going to occur every time the terminal side on your unit circle hits here. So they would occur every 2 pi, wouldn't they? Every 2 pi. So oftentimes we would write plus 2k pi if we wanted the complete family of answers. Now they wanted only answers in the domain 0 to 2 pi. So what we would do is we'd just select this answer of 0 here.
That's actually -2 pi to 4 pi.
Oh, I'm sorry. Thank you. -2 pi. That's going to make it more exciting. To 4 pi. Open interval
Close
on both ends?
both brackets.
Okay, great. Closed interval. Thank you. So you can see then we go further than what I had said originally. If I'd read the problem right, we'd be all the way out there to 4 pi. And we'd go to -2 pi, wouldn't we, over here? So we want all the answers then. So actually using this might be useful, where you then pick different integer values for k. K's are integer values, right? Like -1, 2, 3, 4, 5, 0, or +1, 2, 3, 4, 5. So you're going to have to get the whole family of them, and you can look at the graph and see it easier, but you also could put in here -1, right? -1 would make that a -2 pi, if I put these in order. If I put 0 in right there for k, I get 0 for the result. If I put 1 in there, I see an answer at 2 pi. And if I put 2 in there, I get an answer at 4 pi. So there's the family of zeros. On the graph up here, those correspond to these locations. Whoops.
You didn't do that. There's two possibilities for
Ah,
the sign.
thank you. Boy, you guys are better than I am at this. Okay. So one of the possibilities on your unit circle was here at 0, and the other possibility on your unit circle is over here at pi. Did you notice how I got these answers here, and then what did I do next to see that I made a mistake? I went back to the graph, like I keep saying. Always try to do a graphics interpretation of things, because you can see the mistake that I made by only having that group of answers. By looking at this picture and going, uh-oh, I don't see pi showing up, or 3 pi, or over here at -pi, right? So like Tom mentioned, there's another possibility. Even though it's outside the range on your inverse function, it also occurs over here at pi. So we could have or x equals pi plus 2k pi. See it? Okay, and you've had other types of problems like this in your homework that ask you for a collection of answers outside of just the first domain or range of the function. So doing this one, you can see, you can list your answers here. If you put a -1 in there, let's see, if you put a -1, that would be -pi, wouldn't it? Right? -1 right there gives us -2 pi plus a pi is -pi. If you put a 0 in there, a 0 there, you get pi. Right? Notice the spread between those answers. The spread between them is 2 pi, which you should expect. Jumping from this location to that next one over there, see? At 2 pi. And then similarly, if you put in a k down here of 1, you then get 3 pi. So we get those 3 additional answers. So it looks like we have a total of 7 answers, I believe, showing up. Got it? Yeah.
So the domain for the inverse of sine of 0 is going to be between -pi/2 and pi/2.
Yeah, and this is a function. When you write this, this is a function.
Right.
And there's only going to be one result coming out of that.
Right. Right.
That's why we have to have our brain engaged, because we realize in trigonometry that there's more than one answer, solution possible always. They occur periodically. All right? I don't want to spend too much time on this, but this is old kind of stuff, but yet I know people are a little shaky on some of this, so that's why I wanted to spend time on it. Now here's where it gets a little more interesting. Solve this equation right here. F of x equals 3 halves. Well, you come up here to the problem and you write it down. 3 sine x equals 3 halves, and we want to solve that on that same domain of angles from negative 2 pi to 4 pi. So if you multiply both sides by 1/3, we're going to end up getting that the sine of x equals 1/2. And now rather than going through the inverse sine function, why not just think of your unit circle here? Right? Think of your unit circle, and you know that this occurs, the angle occurs at where the sine happens to be 1/2, occurs at pi over 6. Or every 2 pi thereafter, right? Before or after that, multiples of 2 pi. So again, a 2k pi tossed onto that. There's another pair. Here's your unit circle, right? Right here is where your 1/2 is. There's your pi over 6 right there. And then every 2 pi. And then you also, as I heard somebody say, there's also this 5 pi over 6 over here, plus 2k pi. So you write down the general family of answers like this, and then you're given a specific range or domain of angles here that you want to stay within, that interval. So then you just start, like I did before, you just start picking different values of k and see what results you get here. Now you can see it off the unit circle pretty easily. This is going to be pi over 6. There's an answer there. And if you go around, if you back off, you're going to be minus 11 pi over 6, aren't you? If you back off 2 pi from pi over 6. And notice that's almost minus 2 pi. So we couldn't go any further backwards. And then let's come forward. Let's add 2 pi to pi over 6, and that would be 12 pi over 6 plus 1 more is 13 pi over 6. Sorry if we're getting messy here. Can I go any further? I'm trying to get out as far as 4 pi. I went around one additional time. If I put a 1 in here, that's where I get that 13 pi over 6. If I put a 2 in here, I'm already past 4 pi. Okay? So that looks like, I think that, correct me if I'm wrong, but I think that's just a collection of answers for the pi over 6 multiples. Right? And then come over here. You got your 5 pi over 6. Let's back off. Here's 5 pi over 6. Let's back off by taking 2 pi away from that with a negative 1 down here. So that'd be minus, take 12 pi over 6 off of 5 pi over 6. What's that give you? The difference between 12 and 5? Negative 7 pi over 6. Matter of fact, you see that, folks? Look, isn't that, if you come clockwise, negative 7 pi over 6? Because there's 6 pi over 6 to get here. Back one more is 7 pi over 6. 7 pi over 6, negative. Could we go another 12? No, that'd be too far, wouldn't it? Be outside our domain. And so let's go positive now. Let's take our 5 pi over 6 and add 12 pi over 6. Put a 1 right in here. 12 pi over 6 and 5 is 18 pi over 6, which is 3 pi, right? Doing this all in my head, so it's easy to screw it up.
That's right.
Okay, I think that's right. At 3 pi. And I'm going to check it in a second. How am I going to check this? I'm going to go back to my graph. Take a look at it up here on the graph real quickly. Okay, and then I don't think I can go any further. So I believe we're just going to see 6 answers. Now, up on the graph, we want f of x equaling 3 halves, equaling 3 halves. 3 halves is half of 3. So essentially what we could be doing is like you did in algebra class, is you could do a graphic solution of this by looking for the intersection between that red horizontal line at 3 halves, y equals 3 halves, and 3 sine x. So you're looking for these intersections. And look at the picture here. We see 6 answers showing up right there, corresponding to these jumbled answers that I have tucked in down here. All right? Oh, it's not 3 pi. Thank you. It's not 3 pi. You see how the graphics helped? 3 pi is a 0. So what did I screw up? Okay, I did my arithmetic in my head wrong, which is a common occurrence. So I'm taking 5 pi over 6 and I'm adding 12 pi over 6 to it. If I write it down, I won't screw it up. And I get, that's 12 pi over 6 right there. Sorry for being so messy today. There's 17 pi over 6. Thank you for catching that. And you see how you can catch it by looking at the graph. So there's your 17 pi over 6 and all the others, the other 6, or the other 5 ones. Okay? Last thing in this question. Where is f of x greater than 3 halves? Well, look at the picture. Between here and here, here and here, and here and here. So if I took these 2 locations right here, this one is going to be at pi over 6, isn't it? And this other one's going to be at 5 pi over 6. And that's an interval, isn't it? So we have an interval between, notice this is an open interval, because it says where is it greater than, not greater than or equal to, greater than. So there's an open interval between those 2 points on the graph, and then they occur how often? Every 2 pi, don't they? Don't they occur every cycle? Yeah. So if you added or subtracted 2 pi from this, you'll get those other pair. Or you can look at your pairs of answers down here. Minus 11 pi over 6. Actually, it's not going to be that one. It's going to be this. Yeah, I guess it is. Minus 11 pi over 6. Yep. And then the other one corresponding to this would be minus 7 pi over 6, right here. Corresponding to those locations right there. You can see how that fits in with these. And then the last set over here would be our 13 pi over 6, just past 2 pi. And the last one just before 3 pi is here at 17 pi over 6. Corresponding to those spots. Again, open intervals where the function value is greater than 3 halves. Okay, that's a pretty important concept. That's the reason I wanted to take time going back over this with you. Okay. All right. Let's do a quick introduction to vectors on this same segment, and it'll only take a couple minutes to do that, and then we'll go on and actually start doing the vector business. Okay. Let's see. You've all been in have everybody been on a river before in a boat? Everybody? If not, imagine that you have been, okay? So let's say here's your river, the edge of the river. Let's say the river is flowing this way. Okay? How about, let's say you're up on the McKenzie River in the springtime when the water's really coming through there. Let's say it's moving in a pretty speedy spot at, say, 6 miles per hour. Right? You know, you getting your boat out here, and you're just going to be drifting down that river pretty close to 6 miles an hour, going with the current. Okay? But you're going to get in your boat, and you're going to point your boat straight across the river. Straight across the river, this way. And let's say you're in a kayak. Okay? So you start paddling your kayak, and let's say you're feeling a little lazy. You're paddling your kayak at 2 miles per hour straight across the river. Do you go straight from this spot on the shore over here and end up over here? No. Heck no. Okay? You're going to drift. That's why they call some of those things drift boats. Okay? So you're going to be drifting. You're going to be moving horizontally across the river at 2 miles an hour, but at the same time, the river wants to take you close to its river's flow rate down the river, right? So your path is going to be 6 miles per hour heading down the river, at the same time 2 miles an hour across the river, right? And so what path would you take? Diagonally. And do you notice, let me draw this to scale. So you've actually, in your life, you've done this. And you have a sense of what's going on here, and it is a vector, is what we're talking about here. If I draw this to scale roughly, in 6 miles per hour, you're going to be heading at an angle, aren't you? Like this. Isn't that the path you're going to follow? Right there, even though your boat's pointing straight across the river, you're going to be coming down the river while you're simultaneously ferrying your way across the river. And that thing is called a vector. It's not that tough, is it?
So
But
is it just a triangle with
Yeah.
ratios for lengths?
Yes, it's a right triangle. It's a right triangle with ratios.
It's always a right triangle.
Yep. And what we say, to be fancy about it, is we call them orthogonal vectors, perpendicular to each other. Perpendicular to each other. Whoops, like this. Okay? Whoops, 6, there we go. 6, 3, or 2, right? And the effect of that is moving that way. Same thing happens when you're in a sailboat or something like that, and the wind's blowing, not in the same direction you're going, but you're heading at an angle to the wind or something. You're going to have a drift. You're going to have a drift effect going on. Okay. So here's the trig that goes on here. We have an x component, and we have a y component, and the y component happens to be equal to 6. The x component happens to be equal to 2. And the vector path is this diagonal through there. So how do you write this in math language? We'll get to that in the next segment. Isn't this exciting? Okay. Let's say this is a wide river to make the problem easy. Well, let's see, I could probably do this. Yep. Let's say it's 2 miles wide. How long would you be paddling to get from one side to the other side? An hour, right? If it's 2 miles wide, you have to go somewhere else in the world to find that kind of river, okay? All right, more like a bay or something with a current flowing through the bay. So it would take you an hour to get across there, wouldn't it, to travel that 2 miles, right? To travel the 2 miles. And it would take you, in that 1 hour, you would have drifted 6 miles downstream, wouldn't you? Right. So you can see that this is going to be proportional. If the stream was something less than 2 miles wide, then it's just going to be proportional. You're still always going to be on that heading. So here's the way we could write this vector for our velocity. We have to separate, I'm going to go ahead and show you the math on it. We're going to have to separate the x part from the y part. And oftentimes we do this, and instead of putting parentheses on that, which would make you think you're at a point, right, at a location, x, y, we're going to put something like this. And rather than labeling this y, I'm going to call this v for velocity with a subscript y. And up here, I'll call that v with a subscript x for the x part of the velocity. So here, this velocity vector is going to be made up of a x part and a y part, and we put it inside angled brackets. Now, here's another problem in trying to write this down and make it understandable. This letter right here, v, you might think that that is something that's just a value, like so many miles per hour, like 10 or 12 miles per hour. But you have to have some symbol tagged onto this thing to make this real clear that you're talking about that thing being a vector. And what I like to do is put a little half arrow over the top of it. What you see in textbooks is boldface, but we have a hard time writing boldface on our paper. If you see boldface type on a symbol, that oftentimes is going to mean it's a vector. The other way you see it handwritten is you oftentimes see the symbol of the vector with a bar underneath it, like that. Okay, why don't we stop this segment and just leave it at that as far as an introduction goes, and then in the next segment we'll get on to the vector algebra stuff. All right? Where 3 sine x equals 0 in value, and there are 7 locations where that occurs. There's 7 locations where that occurs. And so, okay, all right. So they got the next segment going, so let's go ahead and get rolling here. So